Okay, let us continue our discussion on symmetries. And today we plan to talk about conserved charges and conserved currents arising from Lorentz symmetry. Okay. And in fact, last time we have built up our expectation on what we should get from Lorentz symmetry, and we saw that we are expecting a conserved current, which we denoted last time by m mu rho sigma, okay, where this mu index is the one which contracts with del mu to give you 0. Okay. So we are expecting a conserved current m mu rho sigma, an object with 3 indices, okay, and in fact we further argued that it should have the following form. In fact, I can go back and show you here, this one. Okay. So we expect something like this. So let's proceed and see what our actual calculation gives. So even though this is a course on scalar fields, I will keep the discussion general in this video and talk about theory which is not necessarily scalar and could contain fields which transform under some representation of the Lorentz group. Okay, and it will be useful because you will see that you get pieces which are present only if the fields are not scalar, and it will be good to see the full result instead of having just seen the special case of scalar fields. So anyhow, let's begin. So I start with a theory which is described by Lagrangian density, this curly L, and there are several fields, so which are labeled by phi A, and I am interested in those Lagrangians which depend on the fields and their first derivatives. Okay, and I am interested in this because you saw earlier that in this case I could write an explicit expression for a general expression for conserved current. Okay, the formula which we wrote earlier. I will write again, but that is valid when this is true. Okay. So you may have several fields, so A runs from 1 to whatever, and here the fields phi A of x, they transform under some representation of Lorentz group. Okay. So phi could be a scalar, or phi could the phi a's could let me write phi a's, they could be scalars. So you may have one scalar, so in that case index A is irrelevant. Okay, did I check whether sound is getting recorded? Yeah, it's getting recorded. And if you have n number of scalars, that's also fine. So each field will be a scalar and they will not mix under Lorentz transformations. Or you could have the phi's could represent A mu's, which are vectors, and so forth. Okay, that's what phi a's are, and so I should specify the transformation property of phi's. So if you have a particular representation, then the transformation property is already specified. So let's say the fields phi A transform like this. So it will transform under some representation, and that representation matrix I denote by S, We have already talked about this in one of the lectures earlier. And there is a summation over B. Okay, this part is not so important. Here all we are saying is, if I take the fields which are located at lambda inverse x, then under Lorentz transformation they give you fields which are located at x. This part S is telling you how the different components mix under the Lorentz transformation. Okay, for example, how A0, A1, A2 and A3 mix under Lorentz transformation. So that piece of information is encoded in S. Okay, the matrix S whose elements are SAB. Okay, and if you were to have this differently, like phi tilde of x is S times phi b of lambda x, then your S would be related to my S, okay, by a simple transformation that which you can figure out easily. But beyond that, there is no mystery about this. Okay. So what is SAB if your phi's are scalars? So let's say if you have n scalars, phi 1, phi 2, phi 3, so and so forth to phi n, what would SAB be? Okay, so in that case SAB would be just delta AB, right, because there is no mixing between different phi's in that case, and this is true for scalar field. And if you are looking at vector fields, then your SAB would be lambda mu nu. Okay, because in that case your fields will be labeled as A mu's. So your SAB would also carry the indices mu and nu corresponding to these indices, and you know that 4 vectors transform as transform with this matrix lambda mu nu. Okay, that's the definition of a 4 vector. So in that case your SAB would be lambda mu nu. So these 4 cross 4 matrices. Okay, and similarly if it was some other representation, you will have something else here. Okay, for example, we have already discussed about a field in very brief, which is a 2-dimensional representation, and you saw that here you will have 2-dimensional matrices constructed out of polymatrices. Okay, so that's another example. Anyhow, and as always, we are interested in infinitesimal transformation because we are going to do this Noether's theorem. So I am interested in infinitesimal transformation. Okay, so in that case, I can write lambda mu nu. Okay, I am interested in lambda mu nu, not so much because of this reason, because of this region, because of this argument. So lambda mu nu, as we have been writing before, is for infinitesimal transformation, it is identity, meaning no transformation at all, plus an infinitesimal amount of transformation given by this omega mu nu, where you recall omega mu nu is an antisymmetric matrix. So this is an antisymmetric matrix. Okay, but what I want to do is, this will help me later in the derivation. I want to slightly modify the notation and write this as, from this omega mu nu, I want to pull out an epsilon to make it explicit that I am looking at small transformations. Earlier I used to call omega as small, but this time I want to pull out an omega epsilon explicitly and define omega as epsilon times omega bar. Okay, so epsilon is infinitesimal. This is not infinitesimal. This is finite. Okay, and and this is, of course, it has to be antisymmetric. And remember that omega mu nu and omega bar mu nu, they are constant matrices. So the entries in omega mu nu do not depend on space-time parameters. Okay, these are some constants. Okay, because if you choose a Lorentz transformation that is a rotation by some amount, then omega mu nu tells you, it encodes that rotation, right? So it's because you are talking about a fixed rotation, omega mu nu will contain some fixed numbers. Similarly, omega bar mu nu. Or if you are doing a boost by some amount, omega mu nu elements will correspond to that boost, which will be some fixed number, and that does not depend on x. Okay, so these are constants. Okay, so that's good. And maybe on the next page, probably. Yeah. So I want to write the infinitesimal version of SAB matrix. Okay. So SAB of lambda, now lambda I am writing as 1 plus epsilon omega bar. Okay. So this would be, of course, it will have a delta AB. Okay, because if you are not doing any transformation, if epsilon is 0, the components are not mixing at all. Okay, they remain whatever they are. So it has to be delta AB, the first term, and the changes will be proportional to epsilon. Okay, and because epsilon and omega bar come together as a product, this will also have omega bar multiplying it, which comes with these indices. And then the whatever mixing happens, for that I define this matrix sigma. Okay. This is not very standard, but several authors use sigma and some authors use S, but nevertheless. So mu nu I have to contract here, of course, and then the AB index on the left, and this one that also has to be carried by the sigma. Now see, all the indices are fine, but I will also multiply a factor of I over 2. Okay. If you do not multiply, then your definition of sigma is different from mine, but because I have used I over 2 earlier in one of the lectures, I will keep I over 2 here. Okay, and of course there will be order epsilon square terms. Okay, so I have written down the matrix SAB. Then I should be able to write down how fields will transform under Lorentz transformations given this matrix, and that's easy to write. So I am asking how a field will transform under Lorentz transformation. Remember, the tilde was I always used to refer the symmetry transformation. So what would that be? That is phi a of lambda inverse x. Okay, that's the first term coming from here. So what I am doing is I am substituting the expression of S that I have written, the infinitesimal version of S, in this expression. Okay, so first term is delta AB, so that multiplies phi b and makes it phi a lambda inverse x. That's the first term, and the second term is coming from here. Okay, and this is what you have seen earlier. Maybe I can try to show you. Just, I think it was on page number 152. You see here, this is what we had written earlier. Okay, the same discussion we have had earlier, and that's what I'm using now. Okay. Now, if you had a scalar field, this sigma would be 0, right, because there will be no mixing, there is nothing to mix, or no mixing between different fields. So, this will just be this piece. Okay. So, let me write for scalar fields. Okay. Okay. But here I have lambda inverse x, not lambda x. So, I should find out what lambda inverse is and put in here so that I expand phi b, okay, because this I have to expand around x, okay. And that's easy, because if your lambda is 1 plus epsilon omega, then your lambda inverse would be 1 minus epsilon omega, right? Because when you multiply these two when you multiply lambda times lambda inverse, you expect 1, right? And that you see here, because order epsilon term will cancel, and what you get is order epsilon square, but we have ignored order epsilon square in both of these, so we cannot say about order epsilon square here, and we ensure that order epsilon term is 0. So, up to order epsilon terms, lambda inverse would be 1 minus epsilon omega bar. Okay. So, that is what lambda inverse would be. So, I can write phi of, let us look at this, phi a lambda inverse x would be x mu minus epsilon omega bar mu nu x nu, and that is the transformed field. So, if you put epsilon equal to 0, you are at x mu. So, now it is easy, I do a Taylor expansion. So, phi a of x, okay, here I have just put the indices, I could have dropped the indices also, but to make it explicit I did that. So, minus the change in the derivative of the field at point x times the change, okay, and plus times the change, and the change is minus epsilon omega bar mu nu x nu. So, that is what I put. So, minus I bring back epsilon omega bar mu nu x nu. Okay, let us see whether everything is correct. So, nu is contracted, mu is contracted, so there is no mu in index here, so which is the same here, but I have missed the index a. So, I should have an a here. So, that is how the field will transform. Phi a will, I mean only this part will transform. So, bad choice of words. What I mean to say is, this phi a for infinitesimal transformation can be written like this. Okay, I am sorry for not using the right words. Now, I will find out what phi tilde of x is. So, phi tilde of x is this piece combined together with this one. Okay, and that is easy. Let me see. Yeah. Let me write down the answer, which you can easily derive. There is not much work in that, and then tell you one of the steps which will be needed. So, I am just collecting the order epsilon terms. So, this piece gives you this and this. So, phi of ax, phi a of x, and these two order epsilon terms I collect. Okay, so plus epsilon omega bar mu nu. Okay, and because here your mu and nu are one up, one down, to bring this one down you will use the metric tensor, and that gives you minus eta mu rho. I have taken the minus sign inside. Okay, x nu del rho of phi of x plus I over 2 sigma mu nu AB phi b of x. Okay, this is, let me check whether the expression is correct, x nu del rho phi of x plus I over 2 sigma mu nu AB phi b of x. Perfect, this is right. Okay, so that is how my field transforms. So what are the things which I need to find the conserved current? Let's go back and check. Where is our, yes. So to find the conserved current, I need to know psi I of x, which is just the change in the fields, that I have already figured out. And the second thing which I need to find out is k mu's. And what is k mu? K mu, let me remind you, I think it was on the previous one. Yeah, k mu is this piece. Okay, so Lagrangian density will with the transformed fields will be equal to the original Lagrangian density plus some total derivative term, and this is this k mu which enters here. Okay, so that's the k mu which I want to find out for my present case. And our J mu is this. The signs, you remember, we had chosen these signs so that energy comes out to be correct. So let's go. Okay. So from here I can write down the psi, right, the change in the field, which is this piece, this entire piece here. But now let's find out the change in the Lagrangian density. So we'll come back to this page. So let me write here itself. So psi A of x is omega bar mu nu minus eta mu rho x nu del rho phi A of x plus I over 2 sigma mu nu AB phi b of x. Okay. Now we need to find k mu. Okay, let's do that. Okay. Now all the theories that we have constructed or looked at and that we will construct or you will construct later in your academic career, they would all be Lorentz invariant. Okay, meaning if you, if you are writing down a Lagrangian density, you will construct the Lagrangian density such that it's a Lorentz scalar. That's the requirement you have. Okay, let me write this down. So we are interested in only those theories in which, for which the Lagrangian density is a Lorentz scalar. And by that I mean that if you take the Lagrangian density and transform the fields by taking the fields to be Lorentz transform fields, okay, the way we did earlier, which is phi tilde A of x would be this one. Okay, if you do this, then what you get should be expressible in this form. okay, where the derivative is with respect to the prime coordinate. So maybe I will give you an example and then it will be clear, and also I will tell you what exactly it means. So remember the Lagrangian density for real scalar field, where you had, apart from some factors of half and other things, you had del mu phi. Okay, and let's look at the transformed version of this. Okay, so the transformed version is del mu phi lambda inverse x and del mu phi lambda inverse x. Sorry, this mu should be up. Okay, that is what it means. But now if you take lambda inverse x and define it to be y, and you define the derivative with respect to y as delta, let me write it, del over del y mu, let's say we call it del prime, then this you can check that this is phi of x del mu prime, phi of y, I have put lambda inverse x as y, and del mu prime phi of y. Okay, so this is happening because it's a scalar. You see, it's easy to understand why this will happen in all the theories which you are interested in. So if you have written down your Lagrangian such that all the indices are contracted, okay, no matter what the Lagrangian contains, what fields it contains and how they transform and how many derivatives there are, okay, if all the indices are properly contracted, then this will happen. This will always happen, that you will be able to write it as the same Lagrangian at y with derivatives with respect to y. Okay, and this is going to happen because look at this piece. Okay. There is an index mu downwards, so it says that this object, for the timing, let's forget about lambda inverse x's. Okay, they are the trivial part of the argument, they don't matter so much. So this index mu tells you that how del mu phi transforms, and it tells you that it transforms like a covariant vector. Now this one has a mu index up which says that del mu phi transforms like a object which has transforms like an object which is contravariant vector. Okay, and these transformation laws for this one and that one are such that they are inverses of each other. And that is why it turns out to be a scalar, because the way this guy transforms cancels with the way this guy transforms, and that's why it forms a Lorentz scalar. Okay, let me remind you, like if you have x square, this x square is invariant under Lorentz transformations. Why? Because when you do a Lorentz transformation, a boost or whatever, x goes to x prime. Okay, x mu goes to x prime mu, x mu goes to x prime mu, but x square remains unchanged, meaning x square still is x prime square, and this is only possible if the transformation property of mu with up cancels against the transformation property of mu down. Okay, and now you can understand, if you are writing a Lagrangian which has fields which themselves carry some indices, okay, even then it's going to work, because if you have arranged for the contraction of all the indices, then you have really arranged for the cancellation of effects of Lorentz transformation, just like here. Okay, let me give you another example. If you have, let's say, f mu nu, okay, where these are f mu nu is del mu a nu minus del nu a mu. Okay, you see that this will also be a Lorentz scalar because everything is contracted. This object will transform under Lorentz transformations in some manner, but this object is going to transform just in the opposite manner, so that the effect of transformation is cancelled. Okay, and that's why it is a Lorentz scalar. Okay, so this is always going to work out. Try to play around with some Lagrangians and try to see if you agree with what I am saying. So, if this is the case, then all the theories which I am going to construct would be of this form. So, they will satisfy this property. Okay, and I am going to arrange this because I want my theories to contain Lorentz symmetry. Okay. So, this is the precise statement of saying that my Lagrangians will be Lorentz scalars. Okay. Okay, good. Then something becomes very easy to understand now. Then this object L, the Lagrangian density, because it's a Lorentz scalar, okay, in this sense, then it's going to transform exactly in the manner in which phi transforms, a scalar field transforms. And how does it a scalar field transform? A scalar field transforms like this: phi tilde of x, which is the transform field, okay, which is phi lambda of inverse x, is just phi of x minus epsilon omega bar mu nu del nu of phi. Okay, that's what we wrote previously also. Then if this is how a scalar transforms, and if I am arguing that Lagrangian is a scalar, then of course Lagrangian density is a scalar, then this Lagrangian density is also going to transform in the same manner. Okay, so I'll look at the Lagrangian density at the transformed fields. And how should it transform? It should transform like this. So instead of phi, I can put L. But now L should be at should be a function of here phi x's. Okay, and the change in the Lagrangian would be, okay, sorry, there is something. Is that correct? Yeah, everything is fine. So here it should be sorry, there is a mistake here. That's why I was thinking something is going wrong. So I have missed a factor of x. I can show you here. No, here. This omega, this mu contracts here, and you have x nu. This x nu I had missed, and instead I had written you here by mistake. Okay, now it's all correct. So what should I get here? I should get del mu of L with again the fields evaluated at x and the derivatives evaluated at x. Okay, and here minus epsilon, the same thing here. Omega bar, mu, nu, and x nu. Nu is contracted, mu is contracted, there is no index, all good. Okay, so that's how the Lagrangian density would change, which means I have the k mu now. That's the k mu for us. Okay, so let's carefully extract the k mu. Let me write it down for ease. So for the class of theories, where Lagrangian density is a function of field in the first derivative, we have written down a explicit form for the conserved current, which was this. Okay, I can make the summation explicit here, minus k mu. Okay, and so let me write down psi a I have written down already, and k mu is the following. So you can see that think psi I wrote down, k mu is minus omega bar mu nu x nu let's go back. So you have del mu of L. So I can take the del mu outside. I can pull it out and put it before x nu. Okay, and I can do so because this will generate a term which will give you 0 when multiplied with the omega bar mu nu. Okay, all you have to use is omega mu nu. This is antisymmetric under mu nu interchange. Okay, and this will generate a piece which will disappear when you contract with something antisymmetric, and that you can see easily why it will happen. Okay, let me show you. So what I can do is take this piece and write as omega bar mu okay, I think there is not even any need to show. See here, this is a derivative with respect to x mu, and when you pull it out here, it will generate a derivative term acting on x nu. So it will give you delta nu mu. Okay, it will give you delta nu mu, and this will be contracted against omega bar mu nu, which is same as omega bar mu nu and eta nu mu. This is a symmetric tensor, this is completely antisymmetric, and that's why that extra contribution will get killed. So I can pull it out here, okay, or in front of this, because omega is a constant. So then you get a minus epsilon del mu times k mu, and whatever remains is a k mu. Okay, so then you can see that k mu will be this. Okay, so now you understand why this is k mu, because the derivative has been pulled out. Okay, and which I can also write as minus omega bar rho nu x nu del mu rho L. Okay, I have written it this way because I wanted the mu index not to be sitting on omega bar. Okay, because omega bars are the parameters and I am going to pull them out eventually. So that's the reason I want to free up this omega bar with from the rho index. Okay, so this is fine. So what's our conserved current then? I just have to plug the expression of where is psi from here, okay, and k from here into this expression, and then I get the conserved current. So let me write down the result. So J mu is equal to minus, and the minus sign is, I think you can check, so I will not explain, del L over del mu phi A. Okay, that's fine. Omega bar rho nu x nu del rho phi A of x. Perfect. Then what? Plus omega bar rho nu x nu del mu rho times the Lagrangian density plus del L over del mu phi A omega bar rho's, okay, maybe I should write it down in the next line, plus derivative of Lagrangian density with respect to del mu phi A. Then you have omega bar rho sigma I over 2 sigma rho sigma a b phi b of x. Okay, let me check if I have written correctly. Okay, let's check first. And one check we can always do is look at whether all the indices are contracted properly, and if they are, it's highly likely that things are correct. Of course, factors of 2 can be wrong, but the signs can be wrong, but at least one level of check would be there. So here rho is, so left hand side has only mu free, so I should have a mu up on the right hand side also. So rho is contracted, nu is contracted, a is contracted because there is a sum over a. I should write here maybe. Okay, and then you have a del mu sitting in the denominator, which is equivalent to having a mu index up. Okay, so if you have a del mu, this means it transforms like a covariant vector, but if you have del over del mu, this object transforms like a contravariant vector. So this mu behaves as if it was on something as an up index. Okay, so that's fine, that matches with what you have here. Here mu is up, which is good, rho is contracted, nu is contracted, so all other indices are contracted, which is fine. And again the mu here behaves as a up index, transforms like an up index, that's good. Rho sigma all gone, a b b, so you have only a as free. Okay, which is not good, but it's all okay because a is contracted here. Okay, so there is a summation over a implied here as well, so I can leave that or I can write out. Okay, so this is the current which we get. Okay, now before I do something more, let's see whether we are happy with this. And of course, you will verify the expression, it's easy, just plug in. But we said that we expect 6 currents, 3 for rotations and 3 for boosts. And what I have here is only 1. So have I made any mistake or is it all fine? Right, there is only 1 J mu. There is, if I put mu equal to 0, I get one charge. It appears like I don't get 6 charges, but only 1. Okay, I will answer it maybe after a little while. So now this these two terms that you see, they appear very familiar to us. Okay, and if you recall, when we were looking at translations, see right now we are looking at Lorentz transformations. Okay, which most we are, because we are connected to identity, we are doing infinitesimal transformations. We are basically looking at rotations and boosts. Okay, because that's the part which is which belongs to proper orthochronous transformations. Okay. But earlier we looked at translations, which has nothing to do with Lorentz transformations. Okay, and in that case we had found that let me write down. Translations gave us the following. So we found that the conserved current which we were writing as J mu rho, and which the standard notation for which is T, okay, and we found that T mu rho was del L over del mu phi A del rho phi A of x. So A is contracted, again there is a sum over A, and mu is up and rho is down, which matches here. and also we had this term delta mu rho times L. Okay, and this piece you are able to see here also, right? It's exactly the same except for this omega bar times x. So if you pull this omega bar times x, what you have here is exactly this piece. Of course, the sign is interchanged, but that's what you have. Okay, so I can write J mu using T mu now, T mu rho. Okay, so let me do that then. So I substitute this expression in here, the expression of J mu rho, and I get the following. So substituting T mu rho from translation symmetry. What do I get? I get J mu is equal to minus omega bar rho nu x nu T mu rho. And then you had the other term, sorry, this one. Okay. Remember, this one comes because of your fields transforming under representations different from scalar representation. Okay. If it was just scalar representation, this term would be 0 and you get only this piece. So equivalently only this piece. But because we are looking at general representations, we get this term as well. Okay, I will leave summation over A implicit. All the things which are contracted are summed over. Okay. Okay, so let's return back to that question whether it's 1 current or 6 currents. You see the omega bars, these are the constants which parameterize how much rotation or how much boost you have done, right? Now you may choose to do only rotation about one of the axes and do no boost at all. So you put all the other omegas to be 0, or you may do a boost along one axis and put all the parameters corresponding to rotations and boost along other directions to be 0. Then you will get one J mu corresponding to that one. So for example, if you choose to put omega 0 1 as non-zero, and of course omega 1 0 because they are related by symmetry. So this is actually equal to minus of this. If you put this as non-zero and all others to be 0. So all omega ij to be 0 and all omega 0 2 and omega 0 3 to be 0. Then you get a conserved current corresponding to this boost. Okay, choosing a different let's say omega 0 2 as non-zero and all other remainings to be 0, you get another conserved current corresponding to the boost along y direction. Okay, and similarly for rotation. So you indeed have 6 conserved currents here, but they all are summed here. Okay, everything has been summed together because of this summation. So we are going to pull them out explicitly in a short while, but there is no issue with this. Okay, let's do a little bit more on the first term. Okay, so let me write the first term and the second term. So this entire thing is first term, this entire thing is second term. So the first term minus omega bar rho nu x nu T mu rho. Okay, minus omega bar, I pull down the index rho downwards, then I will have to pull this upwards. Okay, and if you are not already familiar with this pulling down and pulling up, you can do it by putting the eta matrices explicitly. So you lower it down using a eta, you raise it up using another eta, and then you discover that this is what will get eventually. Okay. So now I know that omega bar is antisymmetric under interchange of rho nu, which means that the piece which this omega bar is multiplying, okay, if I take this piece and write it as a symmetric and antisymmetric piece, and this symmetry antisymmetry is in under the interchange of rho nu, okay, if I write it as a term which is symmetric under interchange of rho nu and a term which is antisymmetric under interchange of rho nu, okay, then because of this antisymmetry of omega bar, the contribution coming from the symmetric part will be cancelled. Okay, so this term or this term can do is sensitive only to the antisymmetric part of this piece, what is written in the round brackets. It cannot say anything about the symmetric part. So to be safe with whatever conclusions we are going to make, okay, and you will see immediately why I am doing this, I should decompose this into symmetric and antisymmetric part, which is I will and drop the symmetric part. Okay, so I am writing it down as x nu t mu rho, okay, plus x nu t mu rho. So that's the same thing twice. So I divide by half. Okay, then I write a piece x rho t mu nu. So what I have done is interchange nu and mu in this. Okay, so that this piece has now become, these two terms are antisymmetric under mu nu interchange. And because I have subtracted this, let me add the same thing back. Okay, so these two cancel and I have already taken care of half, so my expression is same as the above one, so the equality holds. And this one is of course symmetric under rho nu interchange. So if you interchange rho with nu, you get this piece. And as I said, because omega bar rho nu is antisymmetric, this will just kill it. Okay, and I will drop that part. Not drop, but it's not there. And you will see immediately why this was important. Okay. Okay, now I define this object to be m orbital. So I define, so see, this is an object with 3 indices, right? So I define m mu nu rho orbital to be the following: x nu t mu rho minus x rho t mu nu. Okay, this piece. So this becomes minus half omega bar rho nu okay. You see, this is what we were expecting in the last video. Let's go back and check. Here, we were expecting a conserved current with 3 indices, and which was x times t. Okay, you see the rho and sigma. Rho is the first index, a second index on the left. It's the first index here. Okay, and if you go back and check here, it's the same expression. So indeed, we have gotten what we were expecting. At least one of the terms is the same, which is this piece. Okay, and I'm calling it orbital because you explicitly have x here. right? So angular momentum is x times p, and if I put mu equal to 0 here, that gives you the momentum, okay, momentum density. And you see, because it is x times p, it's orbital angular momentum basically, and that's why I have put the label orbital in here. Okay, but I see that my conserved current J mu is not just having an m orbital, which I was expecting in the last video, but an additional piece coming because of this sigma. So if it was a scalar field, then my expectation coincides and I get exactly only this term. Okay, so let me go further and write the J mu which I have found now. So the J mu is minus half omega bar rho nu m mu nu rho orbital minus another term del over del mu phi a I times sigma rho nu a b phi b of x. Okay. Okay. Now, if I take del mu J mu, I should get 0, right, because J mu is conserved current. That's by construction. We are doing Northwell's theorem. So I get minus half omega bar rho nu del mu of this object this should be 0. Okay. But now, because my omegas, they are arbitrary, right? I can choose whatever I wish them to be. Okay, I can put many of them to be 0 or do a boost by whatever amount, rotations by whatever amount. And no matter what I choose the omega bars to be, this has to come out to be 0. So this contraction of omega bar with this object has come out to be 0, independent of my choices of omega bar, which means that this can be true only if this object here is vanishes on its own, right? Otherwise, you cannot arrange that no matter what you choose here, you get a 0. Okay, so since omega bar rho nu can be chosen at will, okay, this has to be identically 0, meaning the conserved current now is this object. Okay, J mu is, instead of J mu, of course you know this object has 3 indices now, mu nu rho. So the conserved current is this m mu, and it carries these indices nu rho. Okay, here it's fine. I have, the reason I was choosing an antisymmetric part was I wanted to drop this piece, because if I don't do that, and if I continue with this piece, okay, and let's say I don't symmetrize and antisymmetrize and drop the symmetric part, and I continue with this, then I would be concluding that here the piece correspondingly will be x nu t mu rho, and I would be concluding that x mu t mu rho minus this piece is J mu. Okay, but that may not be correct, because the symmetric part which is contained in this, okay, our derivation cannot even touch that symmetric part because this kills that symmetric part. So I should be careful and I should include only those parts about which omega mu, rho nu is aware of. Okay, it should not be touching those parts which omega rho nu is not aware of. So this part is fine, and this because it is antisymmetric in rho nu, the sigma also we should have antisymmetric in rho nu. Okay, so you take it to be antisymmetric under rho nu interchange. So I'll interchange the signs and put a plus sign here, okay, to match with the literature. Okay. I mean, sorry, not so much to match with literature, but here nu is second index and rho follows it. So nu comes first and rho later, and that's what I want to have, nu first and rho later, and there is no big deal about this. Okay, there is a contraction over A, contraction over B, and mu is up, nu rho up, three indices here all up, which means all good. Okay, and let me here write m mu nu rho orbital is what? X nu t mu rho minus x rho t mu nu. So we have found all the 6 conserved currents corresponding to Lorentz transformations. Okay, 6 because you have nu rho, and nu rho is antisymmetric under these two indices are antisymmetric under interchange. So there are only 6 independent entries. So that's why you have 6 conserved currents and correspondingly 6 charges. An interesting thing is the first piece is written in terms of translation currents, right? So if you are looking at a scalar theory, all you have is this piece and this term is gone, and then you can write everything in terms of energy momentum tensor. Okay, that is good. Now what? Yeah, and maybe I should remark, is the del mu of this entire thing which is vanishing. So del mu of only this piece is going to be 0 on its own, unless it is a scalar field. In general, if you have to take the del mu of the entire thing and then only put it equal to 0. Okay, let's see if I have more. Yeah, I have more to say. So we have found the conserved current, and I should write conserved charge now. So we have m mu nu rho, yeah, and this is the thing. So, and you remember you have to put J0, right? That integral of d cube, integral of this gives you the current, charge. So we should put mu to 0, and then I get 6 charges, okay, because of this. So what are the conserved charges? They are given by this expression. And of course, d over dt of this entire thing will be 0. Okay. So let's define this object to be J nu rho. Okay. So this J is an object with 2 indices. So this is different from whatever we have been writing. So there is no reason for any confusion. So I will use this notation. Okay. So if I look at what is J0I, these are the ones corresponding to boosts. This is d cube x, okay, m00I, and if I look at what are Jij, then this will be m0ij. And if the field is scalar field, for scalar fields, your j nu rho is integral d cube x nu t0 rho minus x rho t0 nu. Okay. So this gives you the angular momentum. Okay. This one gives you the orbital angular momentum actually, because we are looking at only the scalar part. Okay. Okay, here it is not just the spatial but also the the time nu can take 0 values, 0, and you can put rho equal to I. So this is the generalized version of angular momentum. Okay, but if you look at only the spatial indices, then this is what is coinciding with angular momentum. Okay, so that's the relativistic version of orbital angular momentum. Okay, so that's one object which is one set of conserved charges you get from here, which also, if you put one of the indices to be 0, you see that this conserved charge, which corresponds to boosts now, so I am putting nu to 0, no, I should put I, rho is I, t, nu 0, 0. Okay. You see that time appears explicitly in this. So the conserved charge corresponding to boosts has explicit time dependence here. Say you have an integral over d cube x, but x naught is still there. Okay, and that's why it's you will not use it so much, because it doesn't commute with the Hamiltonian. But this one is of course going to be very useful with the 3 indices. Okay. So what we have seen is that Lorentz symmetry implies 6 conserved currents and corresponding 6 conserved charges, and these conserved charges are for a field that transforms under some representation of Lorentz group. These charges correspond to angular momentum, but the angular momentum has 2 parts. One is orbital angular momentum, which you are seeing here. Okay, but it also has another piece which comes from this term. Okay, and this is, remember why it's coming. It's coming because of this matrix sigma. If it is a scalar, this term is 0, it's gone. But if sigma is non-zero, this term is here. And what sigma does? Sigma is the matrix which mixes the different components of the field phi b. If these are the components, it is, they all are mixed. Okay, so this is intrinsic spin angular momentum. Okay, so this piece of the angular momentum is coming because of something that is intrinsic to the field itself. Okay, it's not coming because of orbital angular momentum. Okay, so if you have for example fields which, let's say electromagnetic fields. Okay, if you have electromagnetic fields, then of course your sigma is not 0, and you know what it is, you can calculate. And then you see, in addition to your electromagnetic fields carrying an orbital angular momentum, they will also carry a spin angular momentum. Okay, something which is intrinsic to the fields, and this you might have already heard of. Or if you were looking at, for example, field theory of let's say a field theory which describes electrons. Okay, and if you are willing to believe me that a field theory of electrons is not described by scalar fields, then you can expect that there also you will get, in addition to the orbital angular momentum, a term which will be giving you an angular momentum corresponding to something intrinsic to the fields corresponding to electrons. And jumping a little ahead, without any proofs or without any concrete arguments, I will just say that if you were to quantize that field which corresponds to electrons, you would get something which will correspond to the spin of electron, because spin is what is an angular momentum, right? So, in addition to your electron having an orbital angular momentum because it is moving in certain way, okay, with respect to the origin, it will also have an angular momentum because of its intrinsic spin, and the reason will be this term. Okay, but at this stage we do not have any particles. I haven't quantized these fields, and I have just done a discussion at the classical level. Okay, so all these currents, J mu and all these things are at classical level. Maybe it's a good point to make one more remark. So, our discussion in the context of Northwest theorem has been purely classical. Okay, means that the currents I have obtained, the J mu's, okay, they have been obtained using classical arguments, and we have found that they are conserved. Now, whether these conserved currents will still remain conserved after we start doing quantum theory is not guaranteed. Okay, it works in almost all the cases except for some anomalies. Okay, but this we should remember. Okay, so this J mu, which is conserved classically, may not be conserved in quantum theory. Okay. So, meaning classically del mu J mu is equal to 0. So, you have found the conserved current, and in some cases, it's not that it is going to break in all the cases, but in some cases del mu, the same J mu will not be conserved. So, this will not happen, but your translations and Lorentz transformations, whatever conserved currents they give here, they are fine, they are going to be good symmetries. Okay. And when this happens, we say it's anomaly. Okay, and if you are more interested, you can look into books in, for example, axial anomaly. Okay. But anyway, that's not what we are interested in further. And this, I think this is all that I wanted to say. Yeah. Okay, then, so let's continue this discussion on quantum fields in the next video.